Swayam Prabha. Digital India. Educated India.
We'll talk about modular arithmetic now, which is a simple idea, but very powerful way. It's a very powerful way of using numbers. So we'll start by defining something called congruence. So we'll say two numbers A and B are congruent to each other with respect to a modulus M if M divides A minus B. Okay, so it's something you can define for any integers A, B, and M. And all you need to know is the notion of divisibility. However, we'll typically be interested in modulus with modulus greater than 0, positive modulus values. And the reason for that is, in particular, if M equal to 0, then congruence with respect to 0 just is the same as equality. So A and B are congruent with respect to 0 only if 0 divides A minus B, but 0 divides only itself. So that means A minus B has to be equal to 0. At the other extreme, if I consider the modulus 1, then any two integers are congruent to each other. That's because 1 divides every integer. So no matter what AB is, 1 divides A minus B. I'll also not bother with negative modulus values because A is congruent to B with respect to, say, a negative modulus M means M divides A minus B. That's the same as saying M divides minus M divides A minus B, right? So I might as well just consider congruence with respect to the absolute value of M. And finally, the congruence is a symmetric relation. If A is congruent with to B with respect to M, then B is congruent to A with respect to M. That's because, again, if M divides A minus B, then M divides B minus A as well. Okay. All right, so that's a definition. You didn't need anything more to understand the definition, but to kind of get a better sense for it, let's go back and look at the quotient and remainder theorem and relate it to this definition. So remember, any number n can be written as qm plus r in terms of a quotient and a remainder r, where r is strictly less than m. So here I'm considering positive m's. So this is r is in the range 0 to m minus 1. And here was an example for m equal to 7. You could list all the integers in this table or calendar, as it were, where the columns are indexed by the remainders and the rows are indexed by the quotients. And there's an infinite table stretching both ways, positive and negative. Okay. And it'll be convenient to denote the remainder by this function. So you read this as a remainder of n with respect to m, or remainder of n when divided by m. Okay. So now, in terms of this, what does congruence look like? So here's a claim. So A and B are congruent to each other with respect to the A and B are congruent to each other with respect to modulus m, if and only if they leave the same remainder when divided by m. So the remainders are equal. Okay. So it's simple enough to prove. So suppose A and B, have remainders R1 and R2 and quotients Q1 and Q2 with respect to M, okay, as given by the quotient and remainder theorem. So this is a unique quotient and remainder. And I can write A minus B as Q1 minus Q2 times M plus R1 minus R2. Now, to prove this claim, I have to go do both directions. So suppose A is congruent with B, is congruent to B with respect to M. So A minus B is a multiple of m divides a minus b. Okay, so I just wrote it as a minus b is some integer q times m. But if that's the case, if this is a multiple of m, this is also a multiple of m. So r1 minus r2 is the difference between two multiples of m. So it's a multiple of m. On the other hand, we know that r1 minus r2 lies in the range, say its absolute value lies in the range 0 to m minus 1. Why is this? This because r1 and r2 themselves lie in that range, and the distance between them cannot be bigger than the m minus 1. So so think of r1 as greater than or equal to r2. So r1 minus r2 is some positive number in the range 0 to m minus 1, which also happens to be a multiple of m. But there is only one such multiple of m in that range, and that is 0. So r1 minus r2 has to be equal to 0. That means r1 equals to r2. In the reverse direction, if r1 equal to r2, if the remainders are equal, then a minus b is q1 minus q2 times m, because this goes to 0. So a minus b is then a multiple of m, and therefore a and b are congruent to each other according to this definition. Okay, so let's go back to this table. And so what does that tell us? So the definition here said a and b are congruent to each other if the distance between them, as it were, so think of this as the distance between a and b is a multiple of m, right? And what we just saw in the previous slide is that it's the same as saying a and b have the same remainder with respect to m. And that, if you look at this table, that's saying that a and b have to fall on the same column, right? For instance, take an example here, 11 and 18, they are congruent to each other modulo 7, because the distance between them is 7. So, to go from 11 to 18, you just had to go down one row in this table, and didn't have to change the columns, because the distance is a multiple of 7. And that's also the same reason why they have the same remainder. They are in the same column, right? So, way to visualize integers which are the same, which are congruent to each other, is to say they are on the same column. Here's another example, 11 and minus 10. The distance between them is 21, and that's a multiple of 7. And again, they both have they both lie in the same column. And since 11 and 18 lie in the same column, and 11 and minus 10 lie in the same column, 18 and minus 10 also have to lie in the same column. Or another thing you can see here is the distance between them is 28, which is a multiple of 7. Okay, so all this is saying the same thing, and a good way to visualize it is that numbers which are congruent to each other are the ones which lie on the same column. Okay, so what congruence does for you is it takes this infinite set of integers and partitions them into these m columns, or what I call congruence classes. So it partitions integers into m classes based on their remainder when divided by m. Okay, so I'll just refer to them as the columns in this table. And now that we have these objects, the columns, right, we are going to define some operations, and that's operations of addition and multiplication, and that's what modular arithmetic is. So fix some modulus m. So fix a table. The table starts off by listing, say the leftmost column is remainder 0, all the way to rightmost column is remainder m minus 1. So the elements of the universe that I'm going to use for modular arithmetic are these columns, right? And I will denote it for the purpose of this lecture by this kind of notation. So A is some element, some integer, and box A sub m stands for the column containing A. More formally, it stands for all x which are congruent to A with respect to the modulus m. Okay, so you could think of that as a set of all elements in that column. And same column can be written in using multiple representative or different elements in the column. So, minus 17, minus 2, 3, they all belong to the same column corresponding to the remainder 3 when you're considering the table with modulus 5. And so these are all referring to the same object, namely this particular column. So the universe that I mentioned here, I'll denote it as Z sub m. It consists of the m columns labeled 0 to m minus 1. Sometimes I'll drop this boxed notation and just simply refer to the columns by their representatives, which are in the range 0 to m minus 1. Okay, so yeah, as I said, we are going to define operations over this universe. So first operation is addition. Yeah, so those are the elements of my universe. And I would define the sum of the column containing A and the column containing B to be the column containing A plus B. Here, this plus just denotes addition as integers. And what I have used that is to define addition over this new universe, Z sub m. So that's a definition. To given two columns, I can add them and get another column. How do I add them? Pick some element in this column, say A, pick an element in the other column, B. Simply add those elements as integers. It falls somewhere in some column, and whatever column it falls in, that is your answer. Okay, so it takes two columns and gives you a column as well. But you should be a little concerned whether it's well defined, because you could have picked any of the elements in the column as its representative A, right, for the first column, and any element in the second column as the representative B. And when you add them, so if you pick, instead of AB, if you pick another A prime, B prime, you would get a different A prime plus B prime. You could get a different A prime plus B prime, right? Which is okay as long as it falls in the same column as A plus B. So do I have such a guarantee? Otherwise, there's not a proper definition. Thankfully, I do. So suppose A and A prime are in the same column. So these two columns are the same, two different representations of the same column. And similarly, these are two different representations of the same column. Then can I be guaranteed that whichever representation I use, so if I use the first one, this is the column I land in, the column where A plus B lives. And if I use the other representation, I will fall into the column where A prime plus B prime lives. Can I be guaranteed that these two columns are going to be the same? And that's not too hard. So what does it mean these two columns are the same? Means A and A prime are, they have the same remainder. So they are congruent to each other modulo m. So m divides A minus A prime. And similarly, m divides B minus B prime. And what we are interested in, then the question is, does m divide A plus B minus A prime plus B prime, right? But A plus B minus A prime plus B prime can be rewritten as A minus A prime plus B minus B prime. So if each of this were multiple of m, then so is this one. Okay, so these questions are indeed answered in the affirmative. So yes, so this is well defined. And the nice thing about modular addition is that it inherits all the nice properties of standard addition. So, existence of identities, right? So if, say, take a equal to 0, so the column containing 0 is, consider the column containing 0 and take a as the element 0, then 0 plus b is just b in standard addition. So you add the column containing 0 to any other column, you'll get back that second column, right? So this column containing 0 is an identity element in this universe of columns. Similarly, there is inverse, it's commutative. A plus b, that I've defined here is commutative because this plus for integers is commutative. So b plus a as columns would be the column where b plus a lives, and a plus b as columns is a column where the integer a plus b lives, but the integer a plus b and the integer b plus a are identical, so they live in the same column. So these two summations, column a plus column b or column b plus column a will give you the same value. So it's commutative. Similarly, it's associative. So all the nice properties you're used to for addition, they are inherited by modular addition. So here is an example of the addition table, right? So here I've dropped the box notation. The table corresponds to a fixed M6. So there are 6 elements in my universe. They are labeled 0 to 5. And, this is just a summation of, 1 plus, so 0 plus anything is the same value. And then, say 3 plus 2 is 5. And 2 plus 3 is also 5. Okay, so this just lists for every row I and column j, you have the modular sum I plus j modulo 6. So if I took 4 and 5, that should be 9, but 9 is the same as 3 modulo 6, right? So I've written 3 here. So this table has entries in the range 0 to 5 as well. Here's another table corresponding to m equal to 5. So this is the modular addition for the table for the modulus 5. And if you stare at it, you would start noticing various nice properties. Some of them are directly inherited from integers, but some of them, so this one is something, kind of, that's there for integers also. For every integer, there is an additive inverse, right, minus a. Same is true for modular addition. So you take 2, its additive inverse is minus 2, but modulo 6, this minus 2 is the same as 4. So it's 2 plus 4, that is 0. Okay. So it might look a little different from the integers you're used to working with, because now you added 2 seemingly positive numbers, 2 and 4 together, and you got back 0, which never happens with integers. But 4 and minus 2 are no different in modulo 6. So you're actually adding 2 and minus 2 in that sense. And more generally, again, this is something true for integers. So if you wrote down an equation saying a plus x equals b, but now this equation is modulo m, so there's an equation in z m, right? And a and b are fixed elements, then you can always solve for x. It has a solution x equals b minus a, right, or b plus additive inverse of a. In terms of this table, what does it say? It says take any a and take any value b that you want to see here. So take a equal to 3 and take b equal to, say, 1. Okay, so then there is some value x such that a plus x equals b. Right. So in other words, you can take any value you want and locate. You will be able to find some cell in this row that has that value, any value in the range 0 to 5, right? So another way to say that is every row is simply a permutation of the values 0 to 5. Okay? So this is something different from integers, and this it is true for integers, except that in integers it's an infinite set. Here we have a finite set, and addition is just a permutation in that finite set. For integers, also addition is a permutation, but it's an infinite set. So it has some of the nice properties of integers, but now the universe is a finite universe. All right, so that's addition. I invite you to stare at these tables and think about whatever patterns you see. You can explain them in terms of the algebra involved. Let's move on to modular multiplication next. So same deal. I'm going to define the product of two columns as the column of the product of some representatives of those two columns. Okay, so this is some column, the column containing some element A, the column containing some element B, and the product is defined as take this A and B, multiply them, see which column it falls in. And again, I'll need to be worried about whether it's a well-defined operation. So whether the column I'm defining as a product, will it stay the same irrespective of which representatives A and B I picked? So here is the question, right? If I pick some two arbitrary A and A prime, which are in the same column but otherwise arbitrary, and similarly some two representatives B and B prime for a column, am I guaranteed that AB and A prime B prime fall in the same column? So suppose A and A prime are in the same column. So I wrote it as I wrote A minus A prime as P times M, and B minus B prime as Q times M. And I'm interested in AB. So and I want to relate it to A prime B prime. So I start by writing A and B in terms of A prime and B prime, right? So I can write A as this PM plus A prime and B as QM plus B prime. I use the distributive property and expand, and I take out a factor of M from all the terms other than A prime B prime, which doesn't have a factor that I can take out. So I leave it as it is, but everything else is some integer times M. So what does this mean? This means AB minus A prime B prime is a multiple of MS, or AB and A prime B prime fall in the same column. They are congruent to each other modulo M. So this is a well-defined operation. So let's take an example. There's a table from before, modulo 7, and let me look at minus 6 times minus 3. So this is minus 6, this is minus 3. Their product is 18. So the product of this column containing minus 6 and the column containing minus 3 is the column containing 18, right? I could have looked at it differently. I could have said, minus 6 is the column containing minus 6 is the same as the column containing 1. The column containing minus 3 is the same as the column containing 4. So I multiply the column containing 1 and the column containing 4. I would end up with the column containing 1 times 4, which is 4. So I'll get back the same column as where minus 3 was. That is the column where 18 also lives, right? So here actually this is an example of minus 6 was the column containing minus 6 was the identity element. It was also the column containing 1, right? So the column containing 1 is the identity of multiplication. And as before, we also have other nice properties inherited from integers like commutativity. So A times B is the same as B times A, and associativity. A times B times C is the same as A times B times C. So here is an example. So same examples as before. So m equal to 6, but now this table is not the addition table, it's a multiplication table. So what happens if I look at 0 times anything, I get 0. So 0 times anything is 0. And 1 is the identity element. So 1 times anything is that thing. How about 2? So 2 times 0 would be 0. 2 times 2 times 0 is 0. 2 times 1 is 2. 2 times 4, so 2 times 2 is 4. 2 times 3 is 6. But 6 is 0 modulo m. 6, the column containing 6 is 0. So I write it as 0. And 2 times 4 is 8, which is 2. 2 times 5 is 10, which is 4 modulo 6. How about 3? 3 times 1 is 3. 3 times 2 is 6, which is 0. Okay, and 3 times 3 is 9, which is 3. 3 times 4 is 12, which is 0. 3 times 5 is 15, which is 3. And you can fill in the rest of the table as well. And so something interesting we saw here is that I took two numbers, say 2 and 3, I multiplied them, and I got 0. The product of two numbers, usually in integers, it's not the case, right? You cannot multiply two non-zero numbers and get 0. And here it can happen. Further, I could take, say look at here, 5 times 5 is 1. That is to say, 5 is the multiplicative inverse of 5. And this never happens in integers, right? You never get in the set of all integers, right, under the normal operation. For rational numbers, yes, you have multiplicative inverses for non-zero integers, but for integers, you don't have, I don't have 1 by 5, 1 divided by 5 as an integer. Whereas here, sometimes that can happen. So here is a number 5 which has, the multiplicative inverse also present in this universe. Here is the example m equal to 5, and here it's even more interesting. All elements other than 0 have multiplicative inverses. So 2 times 3 is 1, and 4 times 4 is 1. So here, if you thought this 5 was actually minus 1, so what you saw here was minus 1 times minus 1 is 1. So maybe that's not that surprising. But here, I have 2 times 3 is 1, and so every number, there are not that many here, but all of them other than 0 have multiplicative inverses. Okay, so that's kind of a very unique property that modular addition has that differentiates it from, modular multiplication has that differentiates it from standard multiplication of integers. But it doesn't always happen, right? So not all elements had multiplicative inverses modular. And when does that happen? Here is a simple characterization. So an integer a, one of those elements in the column, right? One of the columns, a has a multiplicative inverse modulo m if and only if a is co-prime with m. So, and if you think of the modulo 6, 5 had a multiplicative inverse because 5, according to this characterization, that is because 5 was co-prime with 6. Co-prime means they don't have any other common divisors other than 1. So the GCD is the GCD of a and m equal to 1 is the same as saying a is co-prime with m. That's the definition of being co-prime. So the claim here is that this is the exact situation when a has a multiplicative inverse. So what does it mean for a to have a multiplicative inverse? Under the operation, this operation in Zm, it means there is some other element, some other column, or some column, So let's call it U, the column containing U, such that you take the product of these two columns under the operation we defined for columns, you will get another column, the column containing 1, right, the identity element. So the claim is that these two statements are the same, and to see that why that's the case, you can use Bezo's identity from a few video clips back. So it said that, GCD of two numbers can be written as so there exists integers u and v such that au plus mv is the GCD. And further, we saw this as well, the smallest number you can write in this way is the GCD. So you can write the GCD, and if you can write an element, so in this case it's 1. So if we can write 1 as a combination of, as an integer combination of a and m, then the GCD divides 1. So in this case, it has to be equal to 1 because 1 doesn't have any other devices. So if you can, so these two statements are equivalent, right? If there exists two integers uv such that au plus mv equal to 1, then the GCD must divide 1, which means the GCD has to be equal to 1. And conversely, if GCD is 1, you can write the GCD as you can write 1 as au plus mv for some integers. Okay, so these two are equivalent, and I'm claiming that that's the same as this. So let's go in this direction. So suppose there are integers uv such that au plus mv equal to 1. Consider the column in which all these integers fall. mv falls in the 0 column. au falls into some column, which is a product of the column a falls and the column u falls, right? So that's the column this one falls. And 1, there's a column where 1 falls, right?